I'm excited to welcome Professor Prasad Enjeti from Texas A&M, and I'll give y'all a fun story. I was proud to donate the first Bitcoin miner to a university in the state of Texas, which was to Prasad's computer lab. So he's a longtime Bitcoiner before it was cool. He's not just bandwagoning, he's been in the game for a while here. His research is really cutting edge and critically important to Bitcoin mining, not just in the state of Texas, but in the world, and continuing to make it a grid-resilient technology. This is really important work. Please support Prasad. We're fortunate to have him present on this today. So please welcome Professor Prasad Enjeti.
Son? Thank you, Steve. I think... Gigam, I think. We're all A&M people. I think Steve was the first one who got us started off on hey, you need to establish a Bitcoin mining lab in Texas, right? So yeah, we said, yes, we'll do it. And then after that, it has been a roll after that, right? So the presentation today is basically low voltage right through, work with the utility company ERCOT, right? So my name is Prasad Enjeti, but I would like to introduce you to a more famous Enjeti, my son. So right? Everybody knows him. I think Steve was wanting to talk to him about breaking points and so on. So today I was going to talk about briefly 4 points, right? And then so I wanted to actually create a panel with ERCOT people, but they had some travel issues. So I said, okay, let me just present it. So I was going to talk about our mining lab we have established where we can test a lot of Bitcoin miners and then make models and then look at all the utility grid effects. I know many of you are not engineers or electrical engineers, but I'll try to go on the conceptual level. And then what happens when a grid disturbance happens? So grid disturbance happens whenever you have a thunderstorm go by, or a tree falls on the line, or there's so many grid disturbances, right? So that's our Bitcoin mining lab, which we established. So what we have there is a Bitcoin miner under test, right? So that happens to be a Bitcoin miner under test, and then what you have on the bottom is a power source where we can create grid disturbances. So we can make the disturbance of the grid, recorded disturbance, play back there on the power source, and the power source is the one which is powering the miner. So the miner will respond as if it was a grid disturbance, right? And then based on that one, we would build a computer model where we can simulate the entire facility of the miner. Of the mining or AI data center or whatever it is. So based on that, so we have several of these miners in our lab. So it's an ant miner. What's important to see here is that you have a voltage from 200 to 240 volts. So I was going to give you a Bitcoin 101 example. A miner is not just, I want you to just take, the key takeaway is a Bitcoin miner power consumption. I want to have one or two key takeaways of a Bitcoin miner, right? So anybody should understand this. Anybody who's buying a toaster oven or whatever, they should understand it. So here it goes. So if you have 240 volts nominal voltage connected to the miner, it consumes 13.6 amps, 13 amps, let's say, right? Now, for whatever reason, if the voltage goes down to 220, okay, then the current is going up 10% more, 11% more, right? And then if the voltage goes to 200, the current goes up again, right? 16.5. And 180, it goes up to 18 amps, right? So as the voltage goes down, the current goes up, right? This is the characteristic of all the things. So when you overclock the Bitcoin miners, I think facilities overclock occasionally, or maybe more commonly. So overclocking gives you more problems when the voltage goes down, and then the comments are all measured. Yes. I mean, you make the machines work harder and harder to produce more hash rate, I would say, right? Yeah. So that's another minor. And then I'll skip this. So it's doing the same thing. So 240 volts consumes around 14 amps, 14.5 amps. 220 volts, it takes that, and then 180 volts, it takes about almost 20 amps. So so that's actually bad for the grid. It's just drawing more amps. And also bad for the wiring, which you have put in place, and you think you have a wiring which is rated for 14, 15 amps, but now the wiring is rated for 20 amps, right? And if that 180 volts stays there for a minute or two, you're stressing those wirings, right? So there are a lot of things to look into. So these are the voltage and currents. I think I'll skip that. And so that's how the miners are actually connected. So it's a three-phase system. I don't want to explain three-phase here, but it's like a phase A, phase B, phase C, and then a neutral. So in this example, there are about about 95 miners on each phase, and that's usually a typical mining location. So so that's an off-grid mining facility. I think we had some data on the off-grid as well from the Giga guys. So what we understand, 101, the key takeaway is the Bitcoin miner is a constant power load. That means if you give a voltage, the rated voltage, it takes your rated current. And then you reduce the voltage, it takes more current, right? So as you reduce more voltage, you reduce more current, right? So remember, the power is the voltage and current multiplication. That's all. Voltage and current, you multiply that, you get a power. The voltage goes down, the current going up because the power is constant. Okay, that's what I'm trying to say. Bitcoin miner is a constant power load. It's not any kind of a load. Constant power loads are difficult to deal with on the grid because they create negative impedance. Voltage goes down, the current goes up. It's like behave like a negative impedance. Right? If the impedance is negative, then always there is a problem. It's like a slippery slope of breakdown, right? So I just want to remember, so that's our consortium on blockchain and large flexible loads. So I think that picture is from Riot. The picture is from Riot on the day. And then we create some short courses and so on. Our next course is on November 13th. I was inviting Steve on this issue. And the research is mining demand in Texas, carbon footprint, right? Frequency regulation, working in very close collaboration with ERCOT. So that's the price. As the price changes, the mining load is changing in Texas, and so on. So these are some important curves. I want you to just a few key takeaways. So the hashed area is that when the voltage is going down, I explained before, when the voltage goes down, the current goes up. But what happens, the voltage goes down momentarily from to 50% and comes back up right away. Well, if you're outside the zone, the x-axis is the time in milliseconds, okay, and the y-axis is basically the voltage, right? So you can see that in 20 milliseconds, you cannot withstand zero voltage, basically. What I'm trying to say is that the 60 hertz, which have wall socket voltage, if you go to Europe, it's 50 hertz, right? So 1 by 60 is 16 milliseconds, 1 by 50 is 20 milliseconds. So if you lose power for 20 milliseconds, just one cycle, the miner is unable to work anymore, right? And then it'll take a long time to reboot, maybe at least a minute or half a minute to reboot and come back to normal. So that's not very good for the grid, because suddenly the grid lost 300 megawatts of load, and then it takes more than a minute to come back, right? So they have to do a lot of grid adjustments because the frequency kind of oscillates now. So they have to actually do something else with the grid. And then, so in the mining lab, we can create all these grid disturbances and so on. So let me go to the actual waveforms, right? So we'll probably come back to this later. So you can actually see that we created models for the grid, for the ERCOT with the help of ERCOT or for ERCOT purposes. And then when you suddenly take power from 1500 megawatts to let's say 3000 megawatts, then there is an oscillation in the power. The power doesn't just go right away to that point, just it oscillates it. That also causes some transients for the voltage and frequency of the grid, right? And that's our simulation kind of matching that. So these are real grid disturbances on a thunderstorm somewhere in Texas, right? I mean, ERCOT gives us the data, but they don't tell us where the location is, right? So, but they say, hey, for this one, this is at a place where a lot of miners are connected. A lot of miners are connected. So the top waveform shows phase A voltage, right? So phase A current, but pay attention to the middle one. The middle one is a voltage. Some thunderstorm came through, and then you see that phase A voltage start to drop. Okay, and then the y-axis is the x-axis is a time scale in milliseconds, not seconds, in milliseconds. Remember, milliseconds. So phase B is green one. We dropped from almost 100% to 50%. Right, like your lights dim in your house, dimmed in your house. That happens many times when thunderstorms go by. You have lights dim, right, and then they come back up. Sometimes lights dim and turn off completely. That's terrible. If that happens, everything has to be off, right? So lights dim, and then the phase C is actually going a lot more below, right? So when that happens, actually it's interesting to see that, remember what I said, when the voltage goes down, the current goes up. So current is actually going up. The voltage goes down, the current is actually going up in phase A and B and C, and the power is going, and then the current eventually collapses to zero because the feeder cannot supply more than 100% current. So it just collapses. The entire mining facility kind of tripped there after some time. So the bottom one is a power. Power went to almost zero, right? The miner load actually disconnected for a very short disturbance of the grid, and then that's what we are trying to model here. And then why am I trying to say that's a bad thing? So it's like a frequency is something like a table which is rotating, and then a whole bunch of people, heavy people, a whole bunch of people are on the table, and suddenly some 10 guys jump off the table. Then the table will spin faster, the frequency will go higher. Now you need to reduce the spinning force. That means you need to reduce the generation into the grid. So that causes a lot of stability issues for the grid. And that's the reason why we are doing this study. And this is a very important study. And then here you can see the frequency kind of oscillates and then comes back to stable. So it takes a lot on the ERCOT point of view to actually stabilize that frequency whenever you have thunderstorms go back and forth, and then large Bitcoin miners. So coming back to our test results right here, you can see that, you can see that those are milliseconds. If you focus on the 100 milliseconds in the blue one, so the voltage dropped from 1 is 240 to, let's say, about 75.75. For 100 millisecond, the miner turns off, right? But the miner basically turns off. So this is a very important curve which we can produce for several Bitcoin miners, and then you can characterize the whole facility this way. And that's the model, right? That's the model on the computer model, and then these are some of the results. And then this is the curve produced from the model, which kind of almost equal to the real test data. So I guess that's the. We're also working on write-through solutions. So we have a patent on that. I mean, we applied for a patent to write through for large crypto loads, flexible loads, and so on. So if you're interested to work with us, we will be glad to work with you all. And then I think Steve wanted me to leave some time for questions, or he has a lot of questions to ask me, I think. And then. So either I can explain the curves more, or maybe Steve answer Steve's questions or your questions. Yeah.
Thank you, Prasad. If anybody has a question for Prasad, I'd be happy to have you do that. Yes, sir?
Can you please explain to us what is ride-through and what is the purpose that it serves for the grid?
Yeah, right through is, I think right through in layman terms is that you have a load connected to the grid, right? And the voltage is normal, right? If the voltage drops to, let's say, 75% of the original value for 100 milliseconds, the load disconnects. Load should not be disconnecting. It should be riding through. Right?
In other words, if you have a disturbance of the power supply, does the machine stay on?
Machines stay on.
Does it drop?
Machines should continue to stay on and come back. If they get off the grid, then the grid lost a lot of power, right? And then they have to go back and curtail the generation, because otherwise the frequency will oscillate when you have more and more of these connected. So right through is very important. Right through actually is a very important practical problem. Let's say you're pumping, a motor is pumping a liquid, and then you're actually manufacturing some chemical by pumping some liquid, and suddenly there was a dip, not a power failure, power dip, and the motor turns off. That means you need to throw away the entire column of chemical because the reaction progressed in a different direction, which you didn't intend to. And then you have to throw away the entire product. That's in the chemical industry. In the paper industry, again, you have a damaged roll of paper, so you have to re-spool everything. So right through is a very important thing for industry, but also Bitcoin miners too.
Does that mean that the load can stay connected and without a frequency oscillation?
Right.
Okay,
right.
Great, thank you.
Yeah.
Any other questions? Just a second.
Thank you. Hello, my name is Dr. Leah Benamy. I'm with the Education Design Lab. And I'd love to know a little bit more about what the catalyst was for Texas A&M. Oh, can you hear me now?
Yeah, clearly.
I can start over.
Sure.
My name is Dr. Leah Benamy. I'm with the Education Design Lab. I'm a senior ecosystem designer.
Sure.
And we are trying to create more programs that align with this emerging digital economy in Texas. What was Texas A&M's strategy on advocating for this academic content, especially given the uncertainty in this industry with jobs available for Gen Z graduates? What would you say to your peers who are curious but a little hesitant to go into this space?
Again, I need to take this off so I can hear. I don't have to hear myself. But thank you for the question. So as a part of our Bitcoin mining lab, we also have a professor from finance, who teaches like 3 courses. So his name is Korok Ray from the business school, Mace Business School. He teaches 3 courses on Bitcoin mining, right from the fundamentals from the financial aspect of it. And also there are professor in computer science who talks about cryptography and so on. And then in our department, electrical and computer engineering, we talk about the grid and then the vulnerability of the grid and so on. So I think in this lab we kind of go. I think we're covering all the aspects of the crypto industry. Yeah, very collaborative. Of course, our campus is very big, right? So we have 2,000 faculty, 70,000 students, and so on. So these courses are actually available on undergraduate as well, but on the graduate as well. So, and then occasionally we conduct workshops. So we have a workshop coming up on November 13th on this right through and so on. Yeah.
Any other questions, y'all? As a closing, Prasad, then, I'd like to just impart to some of y'all here how important this is, because ERCOT is a quasi-governmental entity that operates the grid on behalf of all of us Texans. So there are political appointees that the governor appoints to run ERCOT, but it operates really, independently outside of the government. And they solicit input from all kinds of stakeholders. Many of you are sitting here, and I know you've been a part of that. But I want you to just talk a little bit about kind of the special relationship that ERCOT has with Texas A&M and why that's important really to all Texans, and that this research isn't kind of just you saying this. It's part of a long history of how ERCOT collaborates with academia and particularly Texas A&M. Can you talk about that, Prasad?
Yeah, thank you, Steve. So, as Steve mentioned, ERCOT is an independent entity there, and then they do. Their aim is to develop models and understand all the, miners as well as AI data centers coming into the state of Texas. And then they need assistance in modeling. So we are part of the large flexible load initiative. So we work behind the scenes because we are more technical, right? So we work behind the scenes with the ERCOT team on modeling. So these are very complex models, trying to make it very simple, and these models need to work accurately. And so that's why we have a lab to test the data, tune it, and then if a facility has some other miners, we will test that and tune that, so the ERCOT can actually study those effects of those miners coming into Texas grid, and then what is the importance of that, versus voltage right through or any of these things, right?
So ERCOT doesn't have like an internal research and development team. This is the ERCOT R&D team.
I mean, I would say ERCOT has good engineers.
For sure.
Right?
For sure.
Has good engineers, so they are constantly working. So we have a big project continuously running with ERCOT. I think so. Large flexible load. We just finished our Bitcoin mining model, and then maybe this week or next week. I thought there will be a press release by now, but it's not there yet. So there will be a press release on the Bitcoin miner model, which is actually a free open source model, right?
That's awesome.
And then now we are already moving to AI data center model. So in AI data center, you have 4 architectures. So we are looking at all the 4 architectures for which the NVIDIA guys want to do. And then after that, we will get into another flexible load called hydrogen electrolyzers. So those are also large megawatt scale power converters, which are connected to the grid, and then making hydrogen from electrolysis, right? Green hydrogen, right? So that's also flexible load, because you can ask them to turn off when you want them to turn off, and you can ask them to start producing hydrogen when the price is low and negative and so on. So
thank you, Prasad. I just encourage everyone, if you can, support his research. I'm a proud Aggie, but it's also important for all Texans. Thanks for the presentation, and keep up the good work, Prasad.
Thank you, Steve.
All right. Thank you, everyone. We're wrapping up here. It's been an awesome day. I appreciate everybody being a part of it and putting up with the headsets. Thanks, guys.